So, my apologies for the delay. Little technical sort of issues at the front with the board, and I might need some help with the oscilloscope later on. So, what we're going to do today is we're going to talk about the timer module and setting up two separate pulse trains on the timer module, meaning effectively we're going to get two PWM signals coming out and we're going to align them differently, either on an edge or on a center. Okay, so I'm going to show you how to get two of these channels working simultaneously together. Now, how many of you have had technical issues with your project so far, trying to get it up and running? Okay, so currently I'm totally empathizing with you because the board is not working like it should be at the front of the classroom right now. So we may have to do some creative debugging in order to get the system working, okay? All right, another question I had for you was what are all of you doing next week? Working on projects. All right, so studying for finals? Everything's due next week. Okay, so I've been trying to figure out, so now we've got this final exam that's going to be happening for this class, we've got a final project for this class, and we have skipped the midterm, right? And we will be having on the scheduled day, which is I believe the 20th of April, it's a Friday at 2 o'clock, we're going to have a grand old time for 3 hours. It'll be so much fun. We're going to have a two-part midterm, or a two-part final exam. Now, for those of you who weren't in the class last time I talked about this, a two-part final exam basically works like this. You spend the first 2/3 of the class, or the 2/3 of the exam, working individually like you would on a normal final exam. For the last hour, you get a different exam, and you get to work on it as a group, or as multiple groups. So it becomes a group exam. And the idea being that when you do the first exam, some of the questions you may or may not get, but in the process of doing the second version of the exam, which is not the same one, it's a slightly different one, the idea will be that you will hopefully learn something in the process so that the final exam experience is also a learning experience. The way this works, and the Faculty of Science has done this for a number of years, the way it works is that if you get a worse average on the group part, it doesn't count for you. If you do better on the group part, it does count for you. So the individual part of it counts for 85% of your exam mark. The group part counts for 15%. So it's not a big part, but it can be significant in order to change your grade from, say, a failing grade to a not failing grade, or a marginal grade to something a little bit better. Does anybody have any questions, concerns, or comments about that? Yeah?
It's right now in the Viva Center, so how are we going to work as a group in that example?
It'll be fun. We're going to come up with some way of doing it. Use a mic. So in the Aviva Center, there are tables, and there's nothing stopping us from moving, at least I don't believe, from moving those tables around. I'll get some clearance or go ahead from the dean before I do it, okay, to make sure that it's all good. But I don't see any reason why we can't, as opposed to a room like this where you can't move the chairs at all. The advantage of the Aviva Center is that you can. Now, what I do have to double check is whether or not talking will be allowed in the Aviva Center. Okay, so I will double check on that. Good question, yeah?
Can you use a laptop or a computer? Is it like an open book or?
It will not be open book.
It will not.
It will not be open book. Yeah. Parisa, sorry, Parisa.
What happened to the midterm mark?
So I'm going to talk about that in a second. Okay, Amir.
Almost the same question. 35% for individual work and 15% for
No, 85% for the individual. 85% for the individual. Yeah, 85. You thought my math was really wrong. Yes, there you go. No. Okay, any other questions? So I got to double check about the Aviva Center, but yes.
What about how will the groups be determined?
Self-selected. You will self-select.
How many person per group?
Doesn't matter. Whatever works for the space that you're in. It honestly doesn't matter to me.
But have you communicated with other people?
So it's a group exam part, okay? And the idea is that it's done in groups, sort of like the flipped classes, okay? So do I have a problem with discussions going on? No, but the Aviva Center question is a good one, and I need to figure out how to resolve that. Okay, so I will look into it. Absolutely, yes?
Would it be much easier to do the exam here, because you said like the group work would be similar to the
Yeah.
classroom?
So that's what I need to look out for, okay? So I will look into it, and I will get back to all of you. But the intent is to do a group exam. Yeah. So if I need to hold it somewhere else, I will hold it somewhere else. Yeah, absolutely. I just need to find a place where 60 people can sit. Okay? Any other questions? Okay, so that brings up the midterm exam. So we didn't have a midterm exam. And I would like to make sure that the final exam is not worth a giant amount of percentage, because you never know what's going to happen, right? And it would be good to have some practice ahead of time so that in case you mess up on one or the other, you've got a chance to recover. So the intent at this point is to have the midterm next week. And what I'm currently trying to do is find out whether we can hold the midterm in here or in the regular lab or one of the other PRISM labs, okay? Either during the class hours or during the assigned lab hours. And the idea would be that it would be a practical midterm. That basically what would happen is I would hand out a piece of paper to each one of you, and it would have a task on it to do with a KL 43. And you would have to do it. Flash LEDs a particular frequency, input a switch to do a certain thing. I'm sorry? Closed book. Yes, it would be closed book. You. I need to figure out how to get maybe portions of the data sheet, okay, or how to print out the part that would be relevant, okay? But the idea would be that instead of a theoretical on paper test, it would be a demonstration test, a little bit like a lab test. Okay? Does anybody have any questions, concerns, or comments about that?
What's the material?
It would be, you have the board, I give you a task, do the task on the board.
I think he's asking what chapters will be on.
So it would cover all of the components that we have dealt with the KL 43, which would mean GPIO, ADCs, timers. That's PWM, yeah, timers.
And not the stuff that we've done before, right?
So the stuff that you covered before, you mean on the 9S12?
Because if we have to cover that as well, we're going to have to look into its specific.
So here's I'm going to reiterate one more time. The idea will be to have a task that needs to be performed on the KL 43 board. So if I were to ask you a question, say on the 9S12, you wouldn't be able to do it on the KL 43.
No, I mean, so there wouldn't be any written part, right? Only
It would be a demonstration of a particular programming task. With some, it's basically a lab test. Yes?
Just to confirm, it will be coding on a piece of paper and not on the actual board.
No, it'll be on the board.
Okay, so how would we program it?
You take the board, you put it on the table, you hook up a USB cable.
Would it be like on our own personal computer?
No, it would be on a lab computer.
That's what I meant.
That's on a lab computer.
Is there an MCU expression on?
Lab computer? Yes. It's installed. Okay. Yes.
But aren't we gonna have access to the internet that way?
So I've been talking to the technical staff about it, and the easiest way to deal with that is to take the Ethernet cable, pull it out, and zip tie it to the post. Done. No more internet. Yes. It's a really easy solution. Okay. So this is what we're going to test in the meantime. Okay, so between now and then we will test it. But the intent is to run on the lab computers and to make sure that you can program the KL 43s as off of them in the lab. Yes.
So can you upload like solutions for like the labs or something? Just something for us to practice with?
So the labs have been out since they've been out, and you are expected to have been working on them since, and so the answer is no. Okay? Yeah.
So, if we go with that route, I'm sorry, my mouth is full, but if we go with that route, would it be possible to get the traditional midterm, the one that was supposed to be out, that we didn't get, as a sample?
No,
Practice for the exam. Since you're not planning to use it.
oh no, I'm planning on using it. It'll be incorporated into the final exam. But I currently have 2 versions of the midterm. So so maybe, I'll consider it. Yeah, I'll consider it. Yes, Adrian.
Will we all be getting the same problem?
No.
So, the difficulty kind of varies.
No, it doesn't. So the idea being that you have to set up an ADC, you have to set up a GPIO, you have to set up a timer, and then you have to demonstrate something that goes along with it. Most of the tasks have a similar number of lines and a similar number of setup steps. So the answer is no. They're not that much more difficult from one another. Since I've done the programming myself, within 20%, they're about the same length of code. Yes?
Do we have access to the reference manual? Or?
I'm going to figure that out. Yeah. Yes, Amir.
With the extra parts, like if you're planning to use an ADC, you give us tools like another sensor or?
I will give you a heads up. So basically, likely what you would have to have is the breadboard and the prototyping board on top of it, which you were expected to have in the lab kit. And then if it was ADCs, then it would be a network of resistors, etc., things along those lines. Yeah.
How will you mark it? Like, for example, say we can't complete the demonstration, but we set up, certain aspects that you require.
Then there would be a proportional mark based on the amount that you were able to complete. Yep. Absolutely. It wouldn't be an all or nothing. It'd be proportional. And there would likely be multiple things to complete. That way, if you can't complete one, then you would be able to complete another. Yeah.
Can I ask a question for the project?
Yeah.
The milestone 2.
Yeah.
So how strict are you with the time limit? Like, what if we're like 7 seconds over, for example? Is that too much?
So either you're on time or you're late.
Okay, so there's no.
You're either on time or you're late. That's how it boils down to.
And how long is the final video supposed to be? Is it also 3 minutes?
It shouldn't be very long. Probably, I have to double check. It'll be in the neighborhood of 3 to 5 minutes. Yeah, not very long. Yeah. Okay? Yes?
You said we can't print our notes, right?
It'll be closed book.
So it's to be exact, it's next Tuesday.
It'll be next week, and I have to determine whether or not it will be during the lab hours or during the classroom hours. But it will be during hours in which you would have been signed up for.
So it would be either Monday, Wednesday, or Friday.
Correct. Monday, Tuesday, or Friday, because Thursday is closed. And actually Monday's open. Friday is open. Friday is open. Friday is on. Yes? Can you use the example code that the IDE uses? The answer is the sample code that is used in the IDE is very different than the code that we're using in class. So I would be very reluctant to actually use it to program if I were you. Yes? Adrian?
So, for example, somebody that has the test on Monday would have a much shorter time to study for this than somebody who has it on Friday. And it's already very short notice.
Yes?
So, with the ongoing strike, we can choose not to cross the picket line for this as well?
That's what people do. And what I will advise you is that the final exam and the midterm exam that will be held during the remediation period will be very different, but equivalent, but very different than what you're encountering this go around. Take it as it is. Equivalent, but different.
Free request. Please don't put it on Monday.
So what I need to do is I need to double check with the schedule of the computers to see when they are available. Okay?
When will you let us know?
I will let you know as soon as I know.
Sir, I think this
Friday, it's not this Friday, it's next week. Okay, so I got to move on. So I need to move on at this point. This Friday is everything is closed. Next week, Friday is open and is a class day. Okay? All right, so now hopefully I'll be able to get the demonstration working by the time magically we get to the end of the period. Otherwise, we're just going to do the coding here. Okay? We'll see. We'll end up seeing what happens. Okay. So when you're doing multiple tasks on the microprocessor, on the microcontroller, you often have to do the setting up of multiple peripheral devices inside of the microcontroller. Okay? What we're going to do today is we're going to set up two of them. We're going to set up, actually going to change the width of that. Now, for those of you who are taking pictures and using your cell phones to capture this, you can totally do that. However, what I've been noticing with students that have been doing that is that you start asking questions about why the code is done a particular way, and you've been taking your pictures without actually taking notes, the stuff that's coming out of my mouth. Okay? And so I'm annotating the notes using verbal cues to talk about particular aspects of the code. It's a really good idea to be taking down notes at the same time. Okay? What I'm writing down on this OneNote application right here will be posted. Okay, that'll get posted just like I've been posting already. What's important is for you to be taking notes about what we're talking about in class, the extras that aren't showing up in writing, okay? So what we need to do is we need to set up 2 PWM channels. And the idea being is that there's going to be a stream or a train of pulses that will come out of this that will either be edge aligned like that, because they align on these edges there and there. You can see it like that. Or they'll be center aligned. Something like this. Okay, center aligned or edge aligned. And the reason this is important, how many of you are doing power engineering, MOSFETs, things like that? Okay. Power conversions, things along those lines, right? When you make a voltage go up or you make a voltage go down, you turn some power lines on and off, right? And you have to keep things in phase or out of phase, right? You have different phases that have to be synchronized. Okay, this synchronizes things. This allows your MOSFETs, for instance, to be synchronized so that depending on what you're trying to do, say for instance, in one scenario, if you're edge aligning like this, you have 2 transistors that are turning on and off. One is connected to plus voltage, the other one's connected down to ground, and you've got some load between them and in some H-bridge configuration. You don't want, in some cases, 2 of the transistors to be on at exactly the same time, or you want to make sure they're off at the same time in order to prevent a short between main power and ground. And depending on how you align these pulses, you can avoid that particular scenario. That's one of the reasons for switching between edge aligning and center aligning, because you can guarantee using this, because everything's nice and synchronized, that you will ensure that there will be none of this shorting out to ground, for instance, of your MOSFETs. This is the reason for making the PWM system on the Kinetis board so much more complicated, because it allows you to avoid issues like that. So the PWM allows you to either edge align on that leading or trailing edge, or to center a line right in the middle of a particular high or low end of a pulse. Does that make sense to everybody? Okay, so that's a feature that I don't believe was actually available in the 9S12 and in a lot of other microcontrollers, but it is one that's available in the Kinetis. Okay, in our case, we're going to connect up two different signals, okay, or two different channels. We're going to do, let's see, D3. So D3 is the D3 connection on the Kinetis board. So it's the D3 Arduino signal. It refers to PTA 12. And that is also connected via the multiplexer to TPM1, channel 0. Okay? So you have the outside port, that's the PTA 12. That's the thing that connects to the outside world. On the inside, you're allowed to switch between things like the timers and the GPIO and ADCs and DACs and all that sort of stuff. In this particular case, if you want to connect to the timer module, the channel that is made available to PTA 12 is channel 0 of timer pulse width modulation unit number 1. And there are 0, 1, and 2 modules that do timing on the system. Make sense, everybody? So that's a hard wiring sort of connection that's available inside. And that is dictated by what keyword that you need to look for. If you're doing the reference manual search, it starts with A, Alt, 0. You look for Alt 0 and then you look up the tables in there and you look for the particular modality or mode that allows you to multiplex to the TPM. Yeah, Simon.
So you mentioned that TPM1 is hardwired.
Yeah.
And I don't believe TPM0 is hardwired.
They all are. So there are individual channels inside of, so we're talking about what's hardwired and what's not. So each multiplexer hardwires to particular channels of different modules, particular channels on the ADC, particular channels on each of the TPMs. Okay? And so it basically allows for, in this case, PTA 12, so port A bit 12, which has a pin on the outside of the chip. It can only connect to timer PWM module 1, channel 0. It can't connect to channel 0 on TPM 0 or TPM 2. It's only allowed to connect to that, and it does that through the multiplexer that's controlled by the pin control register, the PCR.
So if I choose a different port, like port B or port C?
No, it won't. And so what you have to do, and there's some rhyme or reason to it, but I don't know what it is. The only way to figure this out is to go to the data sheet, right? And so here's the data sheet right here. Okay, and if I look up PTA, where's PTA? PTA 12. Okay, so line H628, PTA 12, you see it? When it comes out of reset, it's disabled. Its Alt 0 mode is nothing. Okay, so it has nothing when it's disabled and coming out of reset. Its Alt 1 mode is PTA 12. That's the GPI, sorry? No, that's Alt 1. Yeah. No, it's because you can't see everything on the screen. My screen's kind of small, right? Okay. No, I know. It's that column. Okay, and that's why you always have to scroll up, always have to check, and it's good on you to call me on it. So we check. Okay, don't assume anything, right? So it's the Alt 1. And it defaults at Alt 1 to GPIO PTA port A bit 12. If I go to Alt 2, there's nothing. Alt 3 is TPM unit 1 channel 0. It's right here in the table. That is the only way that you can determine it. Okay? Other questions or concerns? Yeah, Amir.
Alt 3 is TPM1, channel 0? What's TPM?
Yes. It's the Alt 3 multiplexing mode is timer peripheral or timer PWM module 1, channel 0, because there are multiple channels on that timer module. How do I know? It's in the table. You have to look it up. The data sheet, engineers always have to rely on the data sheets. Okay? You move from one chip to another, you go to the data sheet. You move from one architecture to another, you go to the data sheet. You choose one vendor over another, you go to the data sheet. It's always about the data sheets. Always. Okay? So we want PTA bit 12 that connects to TPM1 channel 0, and we know that. We always go to the data sheet to look. The other one we're going to want to connect is the Arduino signal D5, so digital 5 on the Arduino, and this is PTA, and actually, sorry, I'm going to go back over to here. Freedom KL43Z embed. Going to load it up. The reason I chose those two signal lines is because I looked at the diagram, or the picture that's right here. D3, right? D3 is PTA 12, and it has a PWM signal on it. We saw it. I started here. I said I need another PWM. I go to here. I take a look. Port port A5, which is the D5 signal on the Arduino header, and that also has a PWM on it. That's how I started. And then I went to the data book. Okay, so that's what you should be doing during your design phase. You should be doing it that way as well. Okay, so D5 goes to PTA5, and this is going to be TPM0 channel 2. Why channel 2? Because I went into the data book and I took a look. Okay, so let's just make sure that that's the case, because I can always make a mistake. So it's PTA5, TPM0 channel 2. It's up there on the data sheet. Okay? It's not magic, it's referencing your data book. Any questions about that? No? Okay, so that's how we start. I know what that is, and now I got to get everything set up. So how do we do that? We're going to set up one channel, and then we're going to set up the other channel. We set up one after the other. That it's just sequential, just like that. Okay? So first thing I need to do is I need to turn on port A. So I go sim C5, thank you, or equals, and it's going to be the mask sim SCGC5. Let's see, this will be port A, mask, semicolon, just like that. Okay?
We always have to set up a clock every time. Right?
Yeah, and do you remember why? Why we have to set up that clock every time?
Yeah, it was already disabled.
It was disabled, and so this clock, it doesn't make the timing happen, but it does enable the system to work. It's basically a switch. Yes, it's an on-off switch effectively. Okay, so then we do that, and then the next thing that we have to do is we have to set up the alt mode. We have to set up the mux. Okay, so it connects to the timer. So what we do is we say port A, pin control register. So we're dealing with pin control register, and we're looking at bit 12, right? And then we're going to set this to alt 3. I'm going to write it out in binary. 0B, so it's explicit. 0, 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's right. There's 12 bits. 1, 2, 3, 4, 5, 6, 7, 8. And I believe it's bits 10, 9, and 8 right here that control that mode. Because if you look at this, actually, hold on. Okay, so I believe that's the, yeah. So it's bits 10, 9, and 8 that control it. Yes?
How do you know is 1098 is also in the manual?
It's in the manual as well. Okay.
We just go to the alt 0.
It actually comes out as a 3, I believe, in hex. if you work it out. Yeah, because actually, if you look, sorry, right here, this is 4 bits right here. That's a 3. That's a 0. And that's a 0.
Would all 4 just be 4, 0, 0?
It is. Yeah.
Is that a coincidence or is
Well, I guess maybe it's a coincidence. Probably not. Okay. Well, it's a coincidence based on which bits have been chosen to allow that to happen. In this particular case, it's kind of handy. Yeah, so it was probably somebody who was a...
all 0 to 7 is just...
So all
I believe so, yeah.
in the manual it says these bits control.
Yeah. So you look in the PCR, and you'll see, if you look in the manual for the PCR, the chapter that talks about the pin control register, it's got the list of which alt modes. So alt mode 0 is 0. I know that. Alt mode 1 is 1. 3 is the one we've got right here, etc. Okay. All right, so we got that set up. So the next thing, so now we've said that port A is going to be enabled. We've now said that at least for bit 12 of that port, we are going to set it up as in the alt mode that we want, okay, which is the TPM mode from the table that we saw. Now what we have to do is set up the timer. Okay, so that's the next thing to do. Okay, so now it's got to look at that timer. So the thing we got to do there is actually turn on the timer. So again, it's going to be system integration module, like that. And then it's going to be SCGC6. So the ADC and the timer module use the system control or status control. I can't remember what the acronym stands for. Number 6. It uses the number 6 one for turning on ADCs and TPMs. Okay. So then we do that, and we go like this. Sim SCGC6. And it'll be TPM, let's see, we said it was 1? Yeah. So TPM 1. Mask like that. I'm just going to verify my code. Yes. Okay. Now, the thing that's a little bit different here is now you get to choose the second clock. Okay? There's another clock that you get to choose at this point. And that clock is the one that actually allows the counting timing to occur inside of the timer. So here what we're going to do is we're going to modify the option register, number 2. So sim S, and we are going to set this to 0, 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6, like that. And this will allow us to connect up the 48 megahertz clock. There is a 48 megahertz clock inside of the Kinetis chip. Yes, question?
Is this particularly toggles it to be on?
So if you turn this into a 0, it turns it off, and this is another way to shut down the timer. So if this register SOPT2 is set to 0 completely, it turns off the timer. So you have a choice of 4 different clocks, if I remember right. Yeah, no, sorry, you have a choice of 3 different clocks and no clock. So 0, 1, 2, and 3. And the first choice is the default, and that's the 48 megahertz clock that's available by default inside of the Kinetis chip. Yes, Brian.
With that line that starts at port A, is the reason why you set off this 1098, is that because you want it on 3? Or optimal 3 or something?
Bits 10, 9, and 8, right there, are the ones responsible for setting up the multiplexer that connect the port, whatever port we're talking about, in this case, port A, channel 12. It is for every port, alt modes 0, 1, 2, 3, 4, 5, 6, 7 all have the same codes right here. So if I want alt 3 mode on port D or port E, it's also going to be this bit sequence. Yeah, but to know which alt mode you need, you go to the data sheet. But typically, not always, but typically, alt 1 is going to be something like GPIO.
Okay.
Alt 3 is going to be the timer. ADC, I can't remember if it's 4 or 7. I'd have to go back to the table and take a look. But they tend to be all in the same column, all in the same alt mode, making it easy to switch between one and the other. Okay? All good? Yeah, Simon.
Is there a specific reason for your, the alt 3 thing? Is there a specific reason? Is a 0x300 instead of 0x400?
Sorry, one more time with the question?
Because last time we were doing the PWM, single PWM, you set your PCR to 0x400.
The PT22, I believe.
So,
It was a different port.
so every time you do it, you generally want to go back to the table and verify that for that particular port, the specific alt mode is the one that you're looking for. You go back to the data sheet and you verify it. Okay, the only rule that you need to follow is go to the data sheet. Always back to the data sheet. Okay? All right. So we've now allowed for the 48 megahertz clock to enter inside of the timer module. That's what we're doing at this stage right here. The next thing we need to do is disable the timer. So what we do is we say TPM1 status and control register. And this means turn it off. Turn the timer off. You have to do this when you go and configure the timer. If you don't do it, it's not going to work. You won't be able to configure it. Does it affect it? It could, but it's not going to affect it in any way that is reliable. Okay, so the configuration is designed in a way that only works properly if you turn off the whole module first. You disable it for the time being. You can't turn off the clock because the clock's required in order to make the registers change, but you have to make sure the timer hasn't started. It's like on a wristwatch, when you set your chronometer off, you just don't, you just wait. You set it up and then you make it go.
So that's a similar idea of how an interrupt works.
Yeah, you disable interrupts, you set it up, and then you enable interrupts. Here, you disable the timer, you configure it, and then you enable it again. It's always about control of the unit, okay, and explicit. Okay, so we've turned it off. So then the next thing we need to do is we need to determine whether or not the system is going to be giving us edge-aligned or center-aligned pulses. And then whether the pulse starts high or the pulse starts low. Okay, so basically at time is equal to 0, does it start like this? Or does it start like, oops, not like that, hold on. That. So that would be edge aligned starting up or starting down. Or does it start like hold on. That. Center and edge aligned up or down. And this is controlled by two aspects of the register right here. Okay, so you go TPM 1 controls, and let's see, in this case the control, we're doing the control for a particular timer channel. Does anybody remember what channel we're using on TPM 1? Is it 12?
2. Oh, no.
12, 2, 4, 6, 8, 2, do we?
For 0,
The GPM one for channel 2.
0,
Channel 0. Okay? Channel 0 is the one that connects to port A12. That's where the channel goes, right here. Okay, so channel goes right there. It took me a while to figure this one out. I was trying to program up the system and nothing worked, nothing was coming out. It took me hours to figure out this was my bug right here, that I'd forgotten the channel number inside. Okay, so don't forget that one. So you put the channel number, and then it is a particular register in here. And every channel has its own one of these control registers. Okay, and I'm going to go to the next line because I've run out of space. You set that equal to. And what this does is it will center a line and it will start high. So basically, that one right there. So we either edge align the pulses or we center align the pulses. We either start the pulse low or we start the pulse high. Those are the two things that you need to configure at this stage. Brian.
Can you give us the configuration for the other ones?
I will. What we're going to do is, afterwards I'm going to show you how this code changes when you go to edge aligned. Okay? And in that 2-minute really fast video that I did, okay, the idea was to do it very, very quickly, but you can pause that YouTube video. There's a pause button on it. And this is where we talk about else B, else A, MSA, and MSB. That's this. So the MS and else bits that I talk about in the video, this is it right here. So there's else A, else B, MSA, and MSB. 4 different setups that you can do right here. And in the video, I show you that in one case, it gives you a 50% duty cycle. In another case, it does nothing. In another case, it does, oh, and then there's one more, there's, and then you also need to have the CPWMS bit, which I set later on, okay? That's, this right here is done later. The centering will be done later. All right. Right. So we've now set up whether it's going to be edge aligned or not, or we've set up whether or not this is combined with another register that happens later, and together they determine whether or not it's going to be edge aligned or center aligned, plus high or low. Now, the next thing you got to do is you got to set up the timer. Count. So the count is coming in at a frequency of how many megahertz? 48 megahertz. In one of the future registers, we're going to set up a prescaler on it to slow down the 48 megahertz. We're not there yet, okay, but it'll happen. So it's actually going to drop down in this example. Just let me sort of plow through this, okay, so we can get to the end of it first, okay? It'll drop it down to 375 kilohertz, but that's in the future stage, okay? Knowing that it's going to run at 375 kilohertz, we now have to say how long it's going to take for the timer to overflow. So the counter is going to run from 0 up to a particular number, and then it will overflow. The caveat here is that only happens with edge aligned. With center aligned, so with edge aligned, the counter goes from 0, say to F, whatever value you want. When it's center aligned, we go from 0, F, and then it counts down again to 0. It goes up, and then it goes down. It counts up, and then it counts down, and then it overflows. The effect of that is to double the amount of time it takes to overflow, which doubles the period or halves the frequency of the output signal. Okay? So in addition to center aligning or edge aligning, this allows you to control even more the amount of time that it takes for the system to overflow or to lengthen the pulses. This is one of the major reasons why we didn't start with the Kinetis chip. And we started with the 9S12, which is way simpler to program. Okay? There's a lot more variation in what you can do, more variables in what you can do with this Kinetis chip. It's a very advanced processor. Lots of options. Yes?
So when you have center aligned, does it count the center of the high and low, or does it just count the center of the high?
So what happens is that it centers on your choice of high or low. So in our case, we chose it to start high. So it centers on that. Okay? The low part is controlled by the next, not this register we're about to put down, but the next one. So there's two count values that we're going to put in here. One is the duration of the count, and the other one is the value at which it transitions from its initial state to the opposite state. Okay? So if it starts high, it transitions to low. If it starts low, it transitions to high. Lots of details to keep in your head. Okay? Once you get going with it, it's not bad. It's just the first time you have to do this, there's like 15 or 16 different variables you have to keep sort of juggling in the air. Okay? But this is why engineers get paid so much. Because you can do it. And this is the sort of control you don't have in an Arduino. Okay? It just doesn't happen. Okay. So we are center aligned. We now have to set up the count. So what we do is we say TPM1 modulus register, and we're going to set this equal to the highest value you can possibly do in a 16-bit counter, FFFF, which is 65,536, I think, or something. Okay? So on center aligned, it actually turns out that it's going to count twice that. So it'll be something like 120,000-ish, 130,000-ish, okay? It will count that at the frequency that is set by the 48 megahertz that has been pre-scaled down by a certain amount, which we will say in a moment is going to be 375 megahertz. Oh, sorry, 375 kilohertz. Every count, every tick happens at one instance of 375 kilohertz. Okay, so that is the duration. Now we have to set up the transition point, which controls the duty factor. Okay, so then we go TPM1, and that's going to be controls on channel 0. Whoops, channel 0. That's what goes in the square brackets right there, and it's going to be .cnv, and that, whoops, so equals. And if I want to make it half, so I want a 50% duty cycle, it's going to be, does anybody remember? 0x7FFF. And that will allow for a duty cycle, an on time or an up time that's going to be 50% of the duration, and an off time that's 50% of the duration, whether it's center aligned or edge aligned. Okay? All right. All right, so then the next thing we have to do, TPM1, now we go back to the status and control register, SC. We turned it off initially by setting it to what value? 0. Now we're going to make it non-zero, and we're going to do three things in here. There are three things that we control inside of here on a normal basis. One is going to be turn on the timer. That's one thing. So 1 bit is associated with that. The next thing that we do is we control the prescaler. So that is the thing that divides the 48 megahertz down to whatever value we can do. And then the other thing is the CPWMS bit, which is the center versus edge aligned bit. If you set that one to 1, it center aligns. If you leave it alone, it's edge aligned. Okay, so three things we control here. So I'm going to do the bit pattern, and then I'm going to explain what's going on in each one of the bits that are important. So we set it equals, we go 0, B, 0, 1, 0, 1, then 1, 1, 1. These 3 bits are the prescaler. And they are 2 to the 0, B, 1, 1, 1. Okay, so in this case, this will go to 128. Okay, so if I set it to 2 to the 0, that'll put a prescaler of 1. So if this was 0b 0, 0, 0, it'll be a prescaler of 1. So I divide 48 megahertz by 1 or 2, etc., all the way to 128. So 1, 2, 4, 8, 16, 32, 64, 128. No?
Sir, so let's say you wanted some lower frequency, like it's very specific, maybe 10 kilohertz or 5, how would you go about it?
Okay, then you have a problem. Sort of. Because there's multiple things you can do here. Okay? But hold that thought. Let me finish this register, and then we're going to get to that. Because you have a lot of control. So let me just finish this, and we're going to get to that question, and we'll get to the next question. Okay? Yeah, unless it's...
How come you have only 7 bits?
1, 2, 3, 4, 5, 6, 7, 8. Hold on. 1, 2, 3, 4, 5, 6, 7. Oh, hold on. Oh, yeah, sorry. No, I missed one up here. My apologies. One right there. Yeah. And typically, if you miss the 0 bits, or bits that are 0 above it, it gets zeroed anyway. Okay? But hold on. Okay, so this is enable clock, or enable the TPM. And then this is the PWMS, which is the center aligning. You set it to 0, it's edge aligned. You set it to 1, and it's center aligned. Okay. Now, at this stage, it's all set up. If you have not paused your debugger, if you've paused your debugger, all bets are off. But if your program's running, you are now generating pulses. Hopefully they don't look crappy like this, but pulses. 50% duty cycle on and off at a particular frequency. How is that frequency set? So we know that the timer is taking little bitty steps at 375,000 hertz. How long does it take to get from there to there? What is the count value? If my counter's running, it starts at 0, and then over here ends at what value? 1 over 128? Okay, that's one guess. Yeah. What else?
4F, the maximum.
So there, and then this would be 0x f f f f, but only if this is edge aligned. If it's not edge aligned, then that is going to be 0. That's going to be 0. That's going to be f f f f. This is going to be 7f f f, and here 7f f f, if you're doing center aligned. Yeah. But if I wanted to change the period, which is just the inverse of frequency, and I can't lower that clock frequency past 375 kilohertz, what do I do? Yeah, make this 50 or some other value, okay? Sorry, in this case, if I do 50, this will actually increase the frequency, right? So if I do this, if my mod value is 50, then this will be faster. Okay? So if you want to do better than this, one of the other ways of dealing with it is to set off an interrupt every time you overflow. Come on. Yep. Ugh.
So since the center one goes from 0 to back to 0, it's got a greater period, right?
So it is slower. Its frequency is going to be lower. If you center a line, it will be half the lowest. It will be half the lowest frequency you can go with edge aligned. So centering allows you a little bit more control. If you fire off an interrupt there, then what you can do is you can accumulate a count off your interrupts and then manually set your GPIO to go up and down based on, for instance, the count that's occurring on your interrupts. That's another way of doing it. Okay, so you have this to drive an ISR, and that drives a GPIO that goes up and down. That's another way of doing it to extend the length. Another way of dealing with it is don't use the 48 megahertz clock. Okay, right now we're taking a 48 megahertz clock and we are inputting it in. There are other clocks available. The slowest clock on the KL43 is 1 kilohertz. You can put in a 32 kilohertz clock as well. So there's a magic 32 kilohertz clock that's available. It's an oscillator, it's a crystal, okay? And a lot of people use it because it's a fine-tuned crystal oscillator that can be used to give you, if you multiply it right, exactly 1 second of increment in a timer using binary counting, okay, in multiples of 2. So if ever you see a 32 kilohertz clock and you're wondering what's that about, it's about trying to get to an exact 1 second time division. That's why they're used. So you can get kilohertz rated clocks as well. It's just we use the 48 megahertz one because it's used for ADCs and other things, okay? But this may sound like it's really fast, but this clock, when you set up your timer right, can be used to be, who's using hobby servo motors? This will get you the 50 hertz clocking that a lot of hobby servo motors want. Yeah, you can do it. Okay, actually you don't even have to center it, I don't think. You can edge a line and you're fine. Okay? All right, other questions, yeah.
Two quick questions. So the center slash edge alignment, this only matters when you're changing the duty cycle on the fly, right? I mean, that's when you know if the TPM with center line or edge line is the new PW.
Okay, so there's a couple of, I want to get to the on the fly part of your question first. Okay? So and because this is actually practical in terms of how you end up using these motors. How many of you are using H bridges? Yeah? Okay. How many of you are varying the brightness of an LED or something like that? So in those cases, what you're doing is you're varying the pulse width of the pulse itself. In order to vary the pulse width, what you have to be doing you have to control the TPM controls 0.CNV, and you set it to equal to something, some value, whatever that value is, and it will make the pulse that you've got wider or narrower. And this can be done without turning off the timer. So you can do this without doing the turn 1 SC is equal to 0. Why is this important? Because you want it to be immediate. You want it to have an immediate effect. You don't have to turn everything off and then turn it back on after some configuration. So you can do this, the while loop, whenever you want. That command can be sent to your motor or to your LEDs and make things brighten or faster without having to do anything else. It is independent of the SC register. Yes?
So you're saying this controls the brightness of the dimming of the LED. So can you demonstrate that? Because last time you showed us it was mostly like blinking, but it wasn't actually dimming or
Okay.
dimming.
So right now, so we've got a couple minutes. So I've either got a choice of doing the other channel or doing that. I think I've run out of time to do the other channel. So let's see if I can actually demonstrate it. Okay. So we're all going to think positive vibes and make sure that the thing is actually flashing like it should be. Okay. Here we go. Hold on. Okay, so here's my code. So it's all the same code that we just did. Okay? All the same thing. And what I've done here, and this is a little trick that you may want to do yourself when you're coding up, I've written what the bit values are right there. It's because that way you don't have to go to the data sheet, you know? Okay, anyway, so I've got that there. And I'm going to take this 0xf, yeah. No, actually, 0x. I'm not going to change that. I'm going to change the prescaler to 0, 1, 0, like that. That is a prescaler value of 2. So 2 to the 2. So yes, 4. Dividing by 4. And that should take, so you had the flashing LED that was on there. It should now flash so quickly that you don't see it. You don't see the flashing. It's just on all the time. Okay. If everything works out the way it's supposed to. And because it's a demonstration, nothing ever works the way it's supposed to. Ever. Oh, totally. And the more eyes that are looking, the more likely it is to fail. Okay, so it's downloading. So while waiting for the debugger to happen, this business of putting the bits up there like I do right there, that was taught to me by a person who actually works for NXP. And when he goes out to see clients, he has sample code with him so that when he needs to run sample code for the client, he can easily make the change without having to go to the data sheet. So this is industry standard practice. Okay, so just keep that in mind. If ever you need to show code to somebody, do it like that. It looks really impressive for your potential client. Okay. All right, so I've turned it on. You all see the LED? It's on, right? Now we're going to change the value, okay? So it's relatively bright. A trick to find out if it's actually flashing, depending on the frequency. If the frequency is low enough, or if it's high enough that you can't see the flashing, but it's low enough that it's in the sort of the frequency that your eye samples at, you take your board and you shake it. like this, and you're going to shake the photons out. If you shake it enough at the right frequency, you'll actually see strips of light in the air turning on and off. Okay, based on the speed that you're moving your arm. It's an easy way without a scope. You know, if you've got a $4,000 scope, that's great. If you're on your kitchen table at Starbucks and you don't have one, shake it. You look weird, but you know, you're an engineer. It doesn't really matter so much, right? Some cell phone cameras can, yes, depending on the frequency. Okay. All right, so that's running right now. So let's go back here and let's change the duty factor. We're going to make the duty factor, which is the CNV value. Well, in this case, my code is for TPM 0, but pretend, okay? I'm going to change it from 2000 to, I'm going to make it 0050. A very short count. So if everything works properly, you should hardly see the light at all.
So is the period the same? Like,
yeah, the period's exactly the same. So the period is exactly the same. The period's the same. The time that it's on,
right, like the pulse width is
shorter. Yep. From a motor perspective, this is the amount of time that current is being applied to the motor.
right.
And so it's actually proportional basically to the power that's being applied to it's averaging out the power to the motor.
So if you wanted to change the actual period, then you would change the 4Fs, right?
Yes. And if you change the period, because you're going from FF to something smaller, it will actually speed up the pulses.
Right.
Yep. Okay, so crossing my fingers, knocking on wood. Is it dimmer? So it's dimmed by a little bit. Let's see if we can make it dimmer yet, or maybe we can make it brighter. How about that? See if it turns off. Oh wait, hold on. Actually, both of these are, no, sorry, you know what? I've actually got both channels on here. Hold on. I think I got it wrong. There. So my battery on my laptop's about to die. Just end it with this. Hold on. Let's try and make it dimmer again. So I'm about to run it. There. That should be a little bit dimmer. Okay, so basically it's a little bit dimmer than it was before. And so that shows you the way of changing the duty factor in order to make it happen. Okay, so I encourage you to test it out. I will get back to you about the final exam, test center, making sure that we can actually do the group exam during that time. Okay, good luck everyone. And I'll be available for office hours on Thursday.
So, do you make a late submission as well for the video? Is that possible?
Is it possible?
Yeah.
So,
Well, is it acceptable?
so I'm asking you to submit.
And you can do that?
Look, the expectation is that I'm expecting most students
Yeah.
aren't going to have it completed.
Okay.
That is normal for this stage. Absolutely 100% normal. So, look, you